Good day, folks. Welcome to my YouTube channel. If you're new here, welcome, and don't forget to subscribe and like my videos. Watch my videos till the end, and do not skip the ads. The returning subscribers, welcome back. Continue doing the right thing. Thank you for your support. Let's cut the chase. This is the Free State Province. It's the October question paper. It's the preparation for the final exam. This is the paper that they wrote. This is the photoelectric effect. It says in the diagram below shows an electron in a hydrogen atom moving between the energy level from E2 to E1, causing the photon to be emitted. Now, this photon is emitted by a visible light which emit 3,4 times 10 to the power 17 identical photon per second. So guys, if you're looking in this diagram, this is the energy diagram. This diagram, it shows the hydrogen atom, its electrons are moving from the excited state, which is the higher energy level, right, to the ground state. So the ground state is the lower energy level, right? So how do you see, even in there, do you see the electrons, they move from the higher energy level to the lower energy level? So when they move from the higher energy level to the lower energy level, the photons and the energy is released. So we call this type of moving from high energy level to a lower energy level, it's a line emission spectra. So what is happening to the energy? There's an energy decrease and there's a frequency decrease, and also the wavelength is increasing. Why the wavelength is increasing? Because of the relationship. The wavelength and the energy are inversely proportional, right? So the number of photons that are released is this, and which means it's also the number of it can mean the number of electrons that are released, but not in this case. So the electrons that are from here, they coming from the excited state to the ground state, which is the lower, is the same number as that one, right? Now guys, the energy level, the energy that this state has, the energy that this level has is that one, and the ground state, it has that energy. So guys, as the electrons, they moving from that, as I've told you, they releasing energy. So when they release energy, so there's an energy decrease from them because it's coming from the higher state to a lower state, right? And there's a frequency decrease, but as they move from there to there, the wavelength is becoming longer. Now the question 10.1, it says define the term photoelectric effect. I'm not gonna. 10.2, it says identify the type of spectrum produced, right? Emission or absorption. This is the emission, right? Because there's an energy released. 10.3, calculate the energy output of the beam. Guys, the energy output of the laser beam. So as the electrons, guys, moving from the excited state to the ground state, they release the energy, but that energy, they release it in terms of what? Of light, right? Now once they release it in terms of light, we want to know that energy change from this energy to this energy. So before we calculate the power, we must know the energy change. So let's go to 10.3. So what we're going to do, we're going to calculate the energy change. The energy change is going to be E2 minus E1. You say the higher energy level minus the lower energy level in order to know the change, which is the amount of energy that was released. So, which is going to be, it's going to be the energy level 2, it's going to be negative 2,99 times 10 to the power negative 18 minus, and then in the ground it's going to be negative 3,31 times 10 to the power negative 18, and then the answer there, it's going to be, when you punch that in the calculator, the answer there is going to be 3.2 times 10 to the power negative 19 joules, right? I hope I make sense by that. Now that we have the energy change, we wanted the output power, right? The output power. Guys, you must remember that the power is equal to joule per second, right? The power is joule per second, which is, it's in other words, it's energy over time, right? Right. It's very important that now, in order for us to calculate, we must know the power. The power is equal to energy divided by time, right? Now, this involves the number of photons, guys. We're given the number of photons. Now, if you remember in the other previous video that I've done, we have the formula that says energy, which is the total energy, right? The total energy is equal to the number of photons times by the energy of photon, or the energy per photon, right? So our total energy is going to be the power, because these photons are emitted per second. So we'll take the what, the power, changing the power, it's going to be the energy, guys. We're going to take the energy and we divide it by 1. So it's going to be the energy divided by time, and then it's the number of photons times by the energy per photon. So the energy divided by time, which is going to be what? A power. How is that possible? Guys, we have the energy in this energy, if we divide it by 1 second, so it's going to be what? A power. So we're going to have power there is equal to number of photons times by the energy of photon, right? So which is now, guys, the energy of photon now, it's the energy that was released when it moves from the excited state to the ground state. Do you see the photons now? That means there are photons that were released with that energy that was released. So the formula now, it will become the number of photons times by the change in energy, which is, this is the energy that we calculated, which is the energy of what? Energy of photons. This is the energy of photon. So guys, now we're gonna have power there, so we can calculate the power. The number of photon, it was what? It was 3,4 times 10 to the power 17. 3,4 times 10 to the power 17, and then we multiplied by the change in energy, which is the energy of photons, which is, it was 3,2 times 10 to the power negative 19, right? And the power, it's gonna be equal, when you punch that in the calculator, it's gonna be 0.10 watts, right? Now let's go to the next question. That's the power, guys. That's the power that this light has there. This light that is released today. Now in 10.4, it says calculate the wavelength of the emitted photon. So we wanted the wavelength of this emitted photon. So how are we going to do that? It's 10.4. So we're going to use the energy is equal to hc over lambda. All right. So we have the energy of the photon, the Planck's constant. These are the constant. We want the wavelength, which is that. So we're going to substitute. The energy, guys, of the photon is this change that we calculated from this. So which is 3,2. It's 3,2 times 10 to the power negative 19 equal to the Planck's constant, which is 6.63 times 10 to the power negative 34 times the constant, the speed of light is 10 to the power 8, and then we divide by that. And then, guys, it's a marathon of maths. We cross multiply there. So our lambda there, it's going to be 6.2 times 10 to the power negative 7 meters, right? Now, guys, let's go to 10.5. I hope that's easy. So that's the wavelength of this photon. Now, in 10.5, it says if the laser with the higher frequency is used with the number of photons emitted in each second change. Yes, it's going to change, but it says write down increase or decrease or remain the same. So it's gonna decrease, guys. From this light that we had a visible light. So this emission line spectra, it was the light that was emitted, the photon was emitting this light, the visible light, with this number of photons per second. But now if it's increased, now is it asking, will the number of photon emitted per second, so if it's increased, guys, this energy now, it has increased now, it's releasing a energy with the higher frequency. So the number of photons will decrease. So the answer is decrease there, guys. That's 10.4, 10.5, right? The answer there is what? Is decrease. Now 10.6, it says explain your answer for 2 marks, right? That is very important today, all right? Now we use the energy, the laser with the higher energy. So with the higher frequency, you will say as the frequency of the light increases, the energy will also increase. Remember, guys, the frequency and the wavelength, they are directly proportional. So from the formula here, the energy and the frequency, they are directly proportional, right? Now, guys, another thing that is important in explaining this, the total power, this power that we calculated here will remain constant. It won't change. The total power, remains what? Remain unchanged, right? Will remain unchanged. The energy of the photon, the energy of the photons, all right, will increase. As I've mentioned, if the frequency increases, the energy increases, that's the energy of the photon increase. The energy of the photons increases. Now, what's going to happen? There will be less photoelectrons ejected, or there will be less number. All right, there's another thing. There will be less photoelectron ejected per unit time. Or you can say there will be less number there will be less number of what? Of photons. Of photons emitted per unit time. Guys, if you use the higher frequency, these number of photons that are released there, this number of photons that are released there, guys, will be what? Will be less. Now, if you use a higher light in this emission, a higher frequency there, even the number of electrons that are moving from the higher energy state to the lower energy state will decrease as well. I hope I make sense, guys. By that, cheers, bye.